Nada, gracias, y a los que estáis en línea también, que son unos cuantos. Por fin nos presento a David López formalmente. David López-Pérez es investigador distinguido, bueno, ha venido con un contrato de investigador distinguido financiado por la Generalitat Valenciana y parcialmente también por la universidad. Y bueno, es una ayuda que no se consigue fácilmente y se ha conseguido porque David tiene una trayectoria investigadora importante. Bueno, ahora os lo contaré directamente, que seguro que lo hará mejor que yo. Viene de una trayectoria previa en Huawei y antes en Nokia. Eso le ha permitido acumular pues, una serie de achievements, logros científicos constantes, ¿no? Bueno, importante de patentes, muy importante, diría, comparado con lo que hacemos nosotros, tiene más patentes que todo el conjunto. O ha firmado por lo menos más patentes que todos nosotros, unas 60. Y tiene un índice H 25 por ahí, que es, si sabéis de qué va el índice H. Entonces, bueno, se ha incorporado felizmente a a.k.a, volviendo a... Me encanta, sí. Creo que... by the way, in favor of many of us, they talk in English because I was about to say that after so many years ago, I forgot to speak in Spanish. Maybe you can speak in English.
In English.
Okay, so I think we better continue.
Yeah. Thank you, Narcis. Hi, everyone. Really a pleasure to be here and quite exciting. It's my first presentation here as a member of the AI team, so I hope it's memorable. The idea here today is to talk a little bit about drones, UAVs, and mostly about wireless communications for drones. Talking about myself a little bit, I just want to emphasize that the research that I'm going to show today is industrial. So this research came when I was in Nokia and Huawei, and it came to answer a few industrial questions around the UAVs that I will introduce later. Basically, the question is always the same: how we can make money out of this technology, right? Just to say a few things, I was a postdoc in King's College in London. I was distinguished member of technical staff in Nokia Bell Labs for 8 years. I was a technical leader and an expert, the expert of the team in Huawei Technologies for 3 years in Paris, and now I'm here at the UPV. So very happy. And this is important, so we need to acknowledge that the work that I'm going to present is not only done by myself. So actually, I have quite a few colleagues that have participated in this UAV research. And I would like to highlight the contributions of two of them, Adrian Garcia and Giovanni Geraci, that they were working with me in Nokia Bell Labs. And then one of them is now in Ericsson, and the other one in UPF in Catalonia. And also the contributions of my dear friends, Lorenzo Galati from Nokia, Minding from Data61, and Emil Bjorten from Linköping University. All right, so this is the outline of my presentation. So I just want to have a short intro to introduce which are the challenges around the UAV communications, why we are studying this, right? And then I want to talk about a few solutions that we propose. One is for 5G new radio, looking into the sub-6 gigahertz frequency band, and the other one is millimeter waves. And then at the end, I would like to talk, if there is time, about the future. So how we see the future of the UAVs, what are the new challenges, and how these two things, the aerial highways and the non-terrestrial networks, can help to shape the future of this technology. All right, so let's go with the introduction. And this is very important in industry. So why we do things, we need to have a clear why, right? And mostly, as I said before, money is an important driver. So back in 2017, the drone was becoming popular, and we saw that it might be widely adopted by everyone, right? And the thinking is the following: if everybody is going to have a SIM card, is going to have a drone, and a drone is going to need a wireless communication, there is an opportunity to make money there for an operator, right? So, and if everybody has a drone, and we are 7 billion people on the air, so it means 7 billion SIM cards is the hell of money. So why not looking into this, how this could work? And that was a little bit the idea. So after talking with the operators, you could identify two clear dreams for the operators. So I'm an operator, Telefonica, Vodafone, etc. the two dreams about the UAV are the following: to see the UAV as an end-user device. As I said, that every UAV is equipped with a SIM card. At that time, you need to handle the payload of the UAV. Let's say that you're doing video, so you will use Cellular to carry the bits of the video, right? So that means a business there, and also to manage the command and control channel of the UAV, the control of the routes, etc., etc. So there's an opportunity there. So of course, the dream would be even better. The dream is to reuse the current infrastructure. So we have an LTE network. Now we have a new radio network. The dream would be to seamlessly reuse the current infrastructure to serve those UAVs and just cash in all the money without any investment. The question is, can we do that? And the reality is that probably not. And that is what I'm going to try to show you later. Another dream is that to have a true mobile network, a network that I can reconfigure, I can move capacity anywhere at a time, right? Something pops up in a given part of the city, I don't have the capacity, but I can move a base station there just to bring the capacity. That is also another dream of the operator. So that can be realized by having this UAV, which has a small cell mounted on the UAV itself. This is a technology that we were studying when we were in Nokia Bell Labs, and this was one of the prototypes. So this was the small cell. Here there was a UAV on top, and this was the solar panels ready to fit the small cell device to bring the capacity anywhere. Of course, this also has challenges. So there are plenty of regulations about where you can position UAVs on the sky. Finding the optimal locations is a challenging problem. Provided a reliable control and command channel is also non-trivial, and the wireless backhaul is an issue. What I want to say basically is that this might be useful. The drone may be useful for the operator because there is these two dreams, right? To see a SIM card in every UAV and make money of it, or to have this more dynamic network that I can re-optimize on demand. And of course, having identified that in 2019, the 3GPP, which is the machinery behind all this money-making infrastructure, creating standards, decided to put together a study to find out which are the relevant use cases for the UAV. So what the UAV would be useful for. Let's say, for example, for direct steering of the control could be used the communication to do 4x4 surveillance using artificial intelligence, etc., etc. So everything that you can do with the UAV or the most relevant use cases and which are the requirements in terms of communication. So if we want to make money out of these businesses, this is what we need to provide in terms of communications. So you can see there is a given latency, a given payload, a given throughput that you need to support, a given reliability, etc., etc. So having identified the business, the experts go and they say, okay, we want to do this. This is the requirements of the communication network. This is what has to be met. Let's work on creating a network that is able to do exactly this, right? And that was in 2019, meaning that there is a serious amount of effort in making this a reality. It's not anymore some people in academia, a few professors. It's an entire industry. Huawei, Ericsson, Nokia, Samsung, you name it. There are many in this 3GPP consortium. Right. So okay. So let us talk about the details, right? Because here is all about research. So let us go with the research. And what is the fundamental challenge of the UAV? So can I reuse the current infrastructure or not? Can I use these LTE networks and three new radio networks that I have out there, the ones that David is deploying, for example, here? Can I use them? So the reality is that there are two main challenges here. So there is one that is the initial access. This is very easy to understand. So if my phone is switched off, when I switch on the phone needs to go through initial access to attach to the network, right? And identify which is the best server, the best router to connect to, the best base station. And usually you connect to the cell that is the strongest, the one that is the closest. But here we have a problem with the drones. So let us imagine, so the problem is the following, is that the current networks are customized to serve the ground users. We deployed networks and optimized them to serve the users in the ground. And you can see this here. So there is a base station, and usually the antenna is down tilted. It's not looking to the horizon, it's looking down because the user is down there. This might be 30 meters high. So usually it's looking down. And when the network is optimized for the users there, you can see that usually the user, the drone here, if it's walking, is served by the main lobe. However, when we go higher and higher, here we have two examples, you are not served by this main lobe. This one is served by the side lobes of the antenna. And the higher you are, the smaller are usually the secondary lobes, and the more the issue you have. Right? So this is quite an issue, that the network is not optimized for the UAV, and you connect only through the secondary lobes. And the secondary lobes, here, this is a very good drawing, I believe. So you can see here when you are at 0 meters, 1.5 meters, sorry. So the main lobe, the main beam is dominant and constantly dominant for 500 meters here. So it's a nice coverage you have there. But when you go at 50 meters, the main lobe is this secondary one. I mean, you see the secondary, the main, the secondary, and the third secondary. So the coverage is less and less. Right? You see 3 because you have 3 secondary lobes here. And here you have 3 because you have the 3 secondary lobes, but with less power. So why is this an issue? So the issue is that you are not connected anymore to the cell that is closest to you. If I'm the base station and the drone is on top of that base station, logically you should be connected to that base station because you are very close. But because the antenna has a knob, it's not pointing up, it's pointing down, you are connected to a cell that might be 500 meters away. And then you need power to power that communication 500 meters away. So fundamentally, you are not doing your best. And power is expensive, you know, now the electricity bills, etc., is a main issue. Second, and very important problem is the handover. So if you move fast in this direction, your communication will be served by the different lobes. And not only that, between lobes there are nuls. You see that it comes inside. So the communication will be fading in strength very rapidly. And that is also a problem because you may be connecting, when you're in the null of this one, you may be connecting to a cell that is 1,000 meters away, and then coming ping-ponging, and then the chances of handover failure is large. This is a research that we did back in 2017, I believe, and later the 3GPP in their study items of UAV already reckoned, this is a text from that study, that the main lobes being connected by side lobes is one of the main issues, right? That was one of their studies. Of course, we put input there, but not. This is not even the main challenge. Even if we solve that, we have a bigger problem with the drone, and the bigger problem is the following: is the interference. Interference is always the main problem, or tends to be the main problem. And the problem is the following. I call it always one too many, but when you are in the ground, so networks are optimized and there is some thinking behind. If you are this guy here making a phone call, you are calling to your mom, for example. So you are usually connected to the closest cell, that could be this one, right? And usually the chances that you are in line of sight or that there is very few obstructions to that base stations is high. So you may have a clear channel, very good to channel the power. And usually the base stations that are far away, 500 meters, 1,000 meters, there is a lot of blockage in between. So meaning that your serving cell is the predominant one and provides much more power than the sum of all the others. And that is designed to be like that. But now what happens when we fly high? So as you go higher and higher, the probability that your neighbors become line of sight is higher and higher. If you go infinitely high in the sky, you would see, if you are in the North Pole and you go infinitely high, you should be able to see in line of sight all the cells of the North hemisphere, right? So the higher you are, the more cells you see in line of sight, and you lose that advantage of the blockage. So let's say that you are connected to only one, and there are 10 that are perceived with roughly the same power, so your signal quality is 1 to 10. If you see 20 neighbors, 1 to 20. So you are highly in trouble. And this was also reckoned by the 3GPP study. So one of the main issues is that usually a user, wherever you are in town, you see around 6 to 7 neighbors at most, in average. While here, the user flying at 50 meters already sees 16 relevant neighbors. So you see many more cells, meaning that those many more cells are going to interfere you when they are transmitting. So your SNR goes to hell, and then you cannot communicate, basically. And this is in downlink, if I'm here, I'm in this UAV, connected to this base station by the side lobe, as I said before. If this guy is talking, carrying a conversation here, is interfering in downlink there. And this guy carrying his conversation here is interfering there. So we have a downlink interference problem to the UAV. So if the command and control channel of the UAV is in downlink, that is, the network is telling 10 right. So if that message disappears because their communication is interfered by the messages of others, the drone may get lost. In simple terms. But we have even a larger problem. A larger problem is that this guy may be doing video in uplink. So he's sending data to the network, to the server. But this communication is an interference to the others. And this is the true problem, because I said, okay, I'm operator A, I'm gonna make money out of the UAVs, I'm gonna go for this. And all of a sudden you deploy this, you didn't understand the problem. And this UAV that you have accepted in your network is starting to generate interference to all the others. And this is a problem because you as a customer, for example, the operator most likely says, I'm gonna increase your bill €1 a month because I'm gonna support a new capability, the UAV. And they are charging you more, and all of a sudden you have a worse service because of the new interference, because they didn't anticipate this. Most likely is that you change the operator, so you have a problem. It's not all bad news. So if we want to make this happen, we need to solve. At that time, we thought at least those two. And the good news is that new radio came with plenty of capabilities. And one interesting capability of new radio that was already in LT is the dual connectivity. Dual connectivity means that you can be connected. This user of this one can have two communications in parallel. So here is depicted by an LT communication and a new radio communication. And the beauty of the first new radio deployments is that it's a non-standalone deployment. So to facilitate the rollout of the new technology of 5G, the idea was that you're going to use the LT core, and every user will have an anchor carrier in LTE, and then the data plane or another control plane might be on the new radio. So all of a sudden, when we deploy new radio, we have the infrastructure to do dual connectivity. And this is good for the drones because you can have redundancy for reliability. You can transmit all the messages twice, let's say, through the two technologies. So chances are that if you combine the messages, you will get a 3 dB gain, or you have other types of diversity. Let's not go into that. But also you can increase capacity because you can transmit multiple messages in parallel. So this was very good. And it helps. Another thing that it helps is the link carrier design. So in LTE, the networks, I don't know if you have a background on this, but these phones, they love to see pilot signals. because you bring out the phone sets for the pilot, and you know where you are, you connect to the network. No pilots means that this device has to be much more complex to find the network. So LTE was designed with that mindset, pilots everywhere. You bring the phone, synchronization is easy. But that is a problem that even if you don't transmit, the pilots are there. And that is a waste of energy, and it generates interference. So the network, LTE is an always ready network. If you want to communicate, the signaling is always there waiting for you. In new radio, in the new design, it's much more flexible because of energy efficiency and because of interference, building in the concept that if there is no user, there should be no signaling around because it's a waste of resources. And that new link array design facilitates to ameliorate that interference that I talked about earlier. So if these networks are not being used because there is no user, they won't generate that interference in the control plane. So that also helps quite a bit. Okay, and until here I told you many stories, this and that. So let us go with a bit more research. So we felt that these things that I talk about was not enough to get those many millions or to enable that business. But we thought that massive MIMO could really help us to solve some of the issues big time. So, and why? The idea is very intuitive, right? So I don't know, again, so LTE, basically, you don't have massive MIMO capabilities. So the antenna usually, in the simplest form, is a radome with a form of a column where you have multiple elements displayed as in a column, and you have a 120-degree sector. And if you have three sectors, you do 360. In new radio, they have this new amazing technology called massive MIMO, that instead of having a column, you have a panel, maybe 8x4, two polarizations, 64 elements, and then you can steer the beam through beamforming in the horizontal domain and in the vertical domain. And not only that, the more antennas I have, analog antennas, well, all the antennas are analog, but the more antennas I have, the thinner that I can focus more the energy. And that results in this concept that I have beams now, and I can steer the beams. So I may afford to have most of my beams looking down because most of my traffic is on the ground, but I can afford maybe to spend some beams pointing in the sky, right? And here you can see the diagram that this one would serve this area, this one would serve this area, and suddenly the drone that was connecting to a very far base station because of the side lobe now is connecting to the closest one through the main lobe, because now the main lobe is pointing up. Right, so here is a summary of the many studies we did, right? There is a bit of thinking behind them, but no need to go over them. So the first question of our boss was the following. Okay, compare an LTE plane network with a 5G new radio. And let me know, and this was before the massive MIMO, sorry, the 5G deployments came. So let me know what can I expect with this massive MIMO, right, in terms of performance. Can I make that money only by deploying massive MIMO? That was the thinking. So we compare an LTE that is based on a column. The antenna is a column with 8 elements, cross-pole, meaning I have 16 elements in reality. And I can multiplex one user per frequency time resource. To one in which I have a panel of 8x8 antennas, 64, cross-pole, so I have 128 antennas. This does not even exist now in the deployment. But we wanted to know if we go crazy with the massive MIMO, are we want to make it or not? So it has 128 RF chains, which is crazy high. The power consumption of this will be serious at the moment. And a 0 forcing precoder. And here's a bunch of parameters to make all these 3GPP compliant simulations that there is many months of work to create this type of tools. And here's just to show you the results. Let's focus. So in the 3GPP studies, basically they define many cases. The 3, 4, and 5 means that In every sector, I have 15 users. 7% of them are a UAV, 25% of them are a UAV, and half of them are a UAV drone. For the easiest case, which means that I have 14 users and 1 UAV per sector, this is the results that we found. The blue is the LT, the single user transmission. So as the drone goes high, the signal quality, so this is the heights, and this is the signal quality. The signal quality is the ratio of the power that you receive of the wanted communication to the sum of all the other communications, the power of all the other communications. And this is the 5 percentile. So the 5 percentile of the distribution usually tell us the performance of the SLH, or the worst performing users, right? So the ones that are really screwed, I'm sorry for the words. So 5 percentile. So we can see that the signal quality is really bad. To communicate, at least in LT, you need -5 dB SNR. Below, you cannot communicate. You won't synchronize. So the SNR is really bad, and as I go high, the SNR becomes worse, because what I told before, you go higher, mostly you see more neighboring cells that are interfering you in line of sight. So communication goes even worse. But when we deploy a massive MIMO, happy days, because the communication is above. When the drone is not very high, the communication is doable, -3.6 above -5, and the degradation because of the height is not that much, because I'm steering the beam following the drone as it goes high. Of course, at some point it goes below. But okay, this is not bad. Massive MIMO, maybe something. But I have to tell you that with this kind of signal quality, you can connect, might be good for the command and control channel to have 100 kilobits per second, but not to transmit the video. So this might be something, but certainly not enough to make money. So we continue. Okay, let's go back. Let's think more about this. And then there is this guy that goes, what if? When we are doing research, it's all about, inventive things or imagining something. What if we deploy a massive MIMO array on the UAV? Not a massive, but a little one. A 2x2 array that allows me to create a beam. And then I'm gonna align the beams of the UAV and the massive MIMO, which already sounds crazy, and it's crazy, but let us assume that we can make this. How much it could give us? It's gonna put us in a better place. It's worth about thinking about this, because what is easy is to deploy an array that is fixed in a fixed position and create a beam without too much steering. That is doable. But if we do the analysis first, if the very best cannot give us what we want, we forget about it already. And then here it was where the true thinking came from us. And I will tell this in a bit. But so another idea that came was, okay, let's wait. If the problem is the interference that comes from the many neighbors, what if we do null steering? So null steering, this is to explain, okay, we make a parenthesis and I explain something else. And I give you a bit of background. At the time that we were doing this, we were working already quite a bit in Wi-Fi and in the company and in the team. And at that time, we were really pushing for this null steering for Wi-Fi. And actually it was considered for Wi-Fi 7 and 11B, and probably now they continue in Wi-Fi 8. So we have all this understanding of null steering. And because the problems of Wi-Fi and the drone, they resemble a bit each other, we thought, okay, how about reusing this technology for the drone? So traditionally, if you want to avoid interference between two access points, if you have a channel of 20 megahertz, the simplest thing is to do 10 and 10, and I split bandwidth, there is no interference. But the problem is I only have half the bandwidth, right? So we all know that according to Shannon theorem, the capacity goes linearly with the bandwidth. So this is good because you avoid interference. But if I have many access points, I have to do many small pieces and the bandwidth is very small. The other extreme is what people is talking now about this cell-free massive MIMO. That is, of course, is the very best. That means that all the base stations in the world or in an area are coordinated and they behave as a massive MIMO array themselves, canceling through zero forcing all the interference. You cannot beat that, but you need all the base stations being connected through a fiber high-speed backhaul. Maybe Ivana with your fiber is possible. It could be expensive though. And and then this was our idea, which is not our idea. This is known for centuries. So the same way you can point a beam to the user, you can point a null. A null means that you don't point any radiation. And if in an array you have 16 degrees of freedom, meaning that you can point 16 beams, you can choose I can point 16 beams and 0 nulls, or I can do 8 beams, 8 users, and null 8 other directions to don't see any interference. Okay, and this has some complications, so you don't need everything connected. In this case, but what you would need is to understand the channel from your cell to the users of your neighbor. And so usually in a communication network, my serving cell knows my channel because I'm connected to it, but all the other neighbors, they don't know my channel because I'm not connected to it. But if a neighbor wants to place a null to my phone, they need to know my channel. And this is not enabled nowadays. Anyway, so the idea was this, that now I place the beam, this one plays the beam, and all the others place a null to me. So this one is serving me, puts the beams, and these two, they place the null. Right? So this would completely remove the interference from the neighbors. And here, okay, we do all these simulations, this and that. And this is the findings. So this is LTE with the antenna in the UAV. This is 5G with massive MIMO. This is 5G with massive MIMO and the antenna in the UAV as well. And this is the massive MIMO, the 5G with massive MIMO with null steering and without the antenna in the UAV. Without. So LTE plus the antenna in the UAV, rubbish. No, we don't care. Like, too bad, really, like UAV downlink. So only 33%. So let's focus on the blue, the urban macro. Like base stations are 500 meters apart. So only 30% of the users can get the command and control channel of 100 kilobits per second. This is the command that controls the drone. Like if you are the pilot. This is rubbish. So massive MIMO, yeah, as I said before, it gives you a good increase, but not all of them can achieve the 100 kilobits per second. Massive MIMO plus the UAV, yes, almost there, like everyone. But I agree that pointing the array in the UAV is complicated. But look at this, the massive MIMO with the null steering, without the UAV using the beamforming capabilities, it gets me there. 99% of the users achieve this 100 kilobits per second. And okay, the world is not perfect. So if we study a urban micro scenario where there is more cells, so here in the urban macro means that the cells are in average 500 meters away from each other. In the urban micro is 200 meters. It means that there are more cells, more neighbors, more interference. And not only that, urban micro, the cells are 10 meters high and here are 32 meters high. So they are more embedded within the cluster, within the city. And of course, that more interference and less signal power because you have more obstructions because the antenna is lower. It penalizes the performance. So we were at that time not claiming that this is a magic solution. It still has cannot provide the full capacity, the full coverage, But if we would need to invest in this technology, our recommendation was that we should pursue the null steering. This is important because, or I like to think it's important because you make these studies not just because the life is beautiful. It's because now you make an informed decision. Okay, my standardization guys. You make meetings. Okay, we agree that null steering is something that we want to pursue. Yes. Okay, let's invest people in understanding what we need to realize in the new technology, null steering, and then we inform the standardization guys to pursue this. So you put the machinery of the company to work in that direction. So we did these studies. Others, they did similar studies, like even within the company, because you want to make sure others were doing measurements, etc. And this is the most important thing of all. So the most important thing of all is not to serve the UAV. The most important thing of all is to serve some UAVs, but make sure that users in the ground remain unaffected. And it's easy to understand that if I had 8 beams pointing down and all of a sudden I take 1 beam to serve the users in the sky, I'm losing coverage in the ground. That is life is like that. I cannot win here. To win here, I need to lose elsewhere. That is a fundamental thing, not normal. So, which is the performance of the ground users? This is what the boss was always obsessed. Okay, but the guys in the ground, the ones that they pay the subscription now, are they affected? And here you can see that even, so this is the CDF, the cumulative distribution function of the downlink SNR of the users, or the ground users. All what I showed before is the UAVs. And here we have the different technologies from massive MIMO to massive MIMO with NAS and blah, blah, blah. Bottom line is that if you see the performance goes down. So, sorry, no UAVs. So the reference is the black. You see the black line is no UAVs. So no UAVs is on the right. And whatever I do placing UAVs, even with the most intelligent technology, there is a gap. And that means I'm losing. And in some of them, I'm losing quite much. So with null steering, though, and if you have only 1 UAV per cell, if I limit the admission of UAVs to 1 UAV per cell, and I use null steering above -5, which is the range I want, yeah, here I'm okay. I could say, okay, maybe they are not that affected. They are not gonna notice it. The high speed guys in the ground, they will use it because they will see it, but they are happy anyway. So they have high throughput. And this is about the uplink performance. And that uplink performance, just to say something, because at the end of the day, what I want to emphasize with this comment that I'm gonna make is that everything needs to square up. And the 3GPP has started already the performance that I need to provide. And for example, here, I'm talking about 2 megabps per second to do video feedback for direct steering control of the drone to provide that service. Just to say, the 3GPP is a kind of 5G new radio is a kind of technology. Others, Wi-Fi, the IEEE could think of other technologies to provide the same service, right? So here the question is whether the 3GPP technology new radio can provide this video feedback for direct steering control. And for that, I need 2 megabps. But to do the AI surveillance, I need 50 megabps. Of course, I need more because it's a video. And it's a 4x4K. So you will see that the numbers that we see in the experiment about uplink throughput, it could help us with the. So this is the uplink throughput of the UAV, megabits per user and per second. And most of the numbers on top are above 2, meaning that I could support that. But there is no way that I can support the 4x4 surveillance, even with this null steering. So as I said, everything has to square up. So here we are not making promises that the NAS steering is gonna fix all the issues. If we want to solve all the issues, we need more bandwidth. More capacity means I need more bandwidth and probably I need to go millimeter wave. So this is the conclusions, and maybe I will go. I don't need to talk about this. So I'll wrap up very soon. So this is millimeter wave. So we study also the millimeter wave case. And here we use the ray tracer, etc., etc. in the city of London. We understand the different propagation behaviors of the millimeter wave. And basically we could see that yeah, throughput. Well, here I don't have the throughput analysis, but the SNRs were much better. And because I have much more bandwidth, the capacity was better. But there was a problem with this millimeter wave. And we knew this problem before, but there is something called regulation. And you should not violate regulation because it goes against the law. And the regulation says as follows: when deploying outdoor base stations here in Europe, it shall be ensured that each antenna is normally transmitting only with main beam pointing below the horizon. And in addition, the antenna shall have mechanical pointing below the horizon when the base station is only receiving. So for receiving, you can be looking up, but for transmitting, you must point down. The motivation behind this is if you radiate towards the sky, you may interfere the satellite systems that are already working out there. So we knew this, but still we carry on the analysis, and the idea is the following: regulation can be changed if there is a good reason, and then if there is money behind it. Like if there is a good business, we shall change regulation. We can lobby for it. But we need to understand first, again, to prepare that machinery, we should understand whether it's worth it or not. And we did millimeter wave studies also for wireless PON and other technologies to change regulation as well. No, but that is a different topic. And in 5 minutes, I go very quickly about what I'm doing here, what I'm planning to do here. And so this was 3 years back. Now I'm afraid that the landscape for the UAVs has changed altogether. And it has changed because the business is different. Regulation has changed, and we know that there will be aerial highways, most likely. Like if you want to, Amazon wants to deliver packets, the Amazon guys are not going to go in the city of Valencia as they please. There will be a highway, aerial highway, where they can go, and they cannot exit that. And also we know that the taxi, the aerial taxi is becoming more and more important. So and the aerial taxi is very different because it won't fly up to 200 meters high. It may fly up to 1 kilometer high or 1.5. A massive MIMO there is excluded because it's so far that the beam, even if it's very narrow, is so far that it opens, right? It's a cone, and a 1 kilometer might be, it's harder to place that NAS and those beams. It diffuses. But there is a lot of money. So 1.5 trillion according to Morgan Stanley. So it's worth thinking about these aerial taxis because there might be a business. And we need to what you need is different. If a person is within the taxi, that person most likely wants to see a video. So in the UAV before is the drone sending the video because you are doing surveillance. But now there is a human consuming videos in the downlink. So the case is different altogether. So aerial highways, I believe on them. I said to my student in Huawei, let's work on this. If you check the literature, there is very, very few about studies about aerial highways. What people has done is very different, and this is very interesting. And some people has made their name with those other studies, but so the game is the following. So if I have a network, which is the optimal route of the UAV to navigate from A to B? So if there is a coverage hole, the UAV will avoid. And I think that makes a lot of sense for, military, for rural. But in a city, people cannot do with the UAV as they please. They need to follow some rules, and there will be a highway. So that thinking is no good. So what we could do is, if we know that the aerial highway is gonna cross the UPV, so we can prepare the network to provide a good service on that route that I know, right? And is optimizing the network for the aerial highway. And we put together some studies, and of course it works because it's just simulation, but to show that, okay, if I model the network, large scale modeling, I have my stochastic optimizer that can go through the shadowing and all this stochasticness of the traffic, etc. We always use Adam usually, and so we could see significant gains. So basically, I think it's 6 dB. So not planning them. So this is the aerial highway, this line. So if I don't plan the network and I attempt to serve these users, and if I know that these highways here and I optimize the network and I serve the users, we saw that you could easily achieve 6 dB gain in the signal quality by just playing with the down tilt. The question is now, what the student is looking at now and others is that, okay, now we have massive MIMO, all these beams. How do we coordinate the beams of the entire network such that we cover the aerial highways? And that is part of what we want to do with this project that I have here. And not only that, also another set of studies we did in the past is that, okay, the NTNs are gonna come. So NTN means a non-terrestrial network. There will be satellites, LEO geostationary, LEO hubs, and drones. How can I use all these base stations that will be mounted on these devices to provide service to the drones and to the drones in the aerial highways? And the satellites might be quite handy to serve those aerial taxis, because I said from the ground it seems not easy by the studies we've done, because with the massive MIMO we cannot point the beams, maybe with millimeter wave, but you have seen the regulation. And just to say that the massive MIMO does not violate the regulation because the panel is looking down. What you put up is the beam, but not the. So. And this we put together an analysis of these satellites, ground-based network, aerial highways, not aerial highway, UAV, and analyzed the capability of the LEO satellites to provide service. And basically, we saw that if you have a proper arrangement and the LEO constellation is quite dense, meaning that usually the satellite is, the elevation angle is 90 degrees on top of you, best coverage, you could do quite nice things in terms of providing the command and control channel for those aerial taxis. And with this one, we got the best paper award this year in Globecon, which I was happy. And yes, so the last one is that I'm hiring people for this. So if you know someone that wants to do a PhD working on this, just let me know. We can make it work. I think it's well exciting, right? You pay. Yeah. We will pay. Yes. Not for free. Not for free. As I said, money is always important for everyone, even for. Right. So, you have any questions, guys? Or... Thank you. That's a nice piece of work. Yes, I have a question about mobility. Yes. So everything is fine until you consider that drones are fast, faster than humans. Yes. So. But maybe GPS, because location is by default in the drone. Maybe the location system GPS helps a lot. So that's a mix of the two questions. Right? No, I get the question. How much GPS helps? So terrestrial. I'm gonna tell you the same things that they told me when I joined Nokia, Alcatel-Lucent at that time. So GPS does not exist for the wireless communications in the sense that the network does not acquire. So the managing entity, the scheduler, all those things, they don't know the GPS. the GPS information is and with the privacy issues that we will see in the future, all these minimization of the drive test tools where the user shares the GPS is more and more concerning. So the 3GPP always try to work in the mobility management without any knowledge of the GPS coordinates. It's mostly RSRPs.
Neither Galileo,
I know, but that is different. That is for synchronization purposes, this and that. That yes, the network for synchronizing and making sure that all the base stations of your network, they start as a frame at the same time. We use clock, and that clock is usually a GPS. So, but to manage, for the mobility management, GPS is not usually used. So I work on this as well, and not for drones, but in a urban macro network, usually the probability of handover failure is around 1 to 2%. So it's non-negligible. Handovers do exist, failures, and if you go with your car and you're carrying a communication, the handover is a problem.
Yes.
And in here, it will be even a larger problem because you are moving faster than a car sometimes, and the side lobes are a killer because you go from this side lobe to the null to the next side lobe very quickly. So you see all these crazy signals that change very fast. So the way that we want to address this, I guess, is through these dual connectivity concepts in which the control comes through a bigger cell that is somehow omni. You could think about the satellites, right? If you provide that control through a hypercell, that high. Yes, so that could solve many of the issues. But this is something that I want to start is one of the 3 work packages, mobility. Mobility with ground cells, because this is a problem. And a serious one. And my answer is that dual connectivity, multi-connectivity in general, multi-RAD, etc., probably is one of the solutions through redundancy. Making sure that you see that channel from different cells at the same time.
Millimeter wave for as long as the drones fly lower than your antennas, or those drone highways have to be
right. So this is a good question. We thought about this. So I think I have a picture somewhere here. So I think the beauty of the drone is if they fly above the cluster of buildings, because if you fly within the cluster of buildings, then you need to navigate through the buildings and be even more intelligent. It's not from A to B, the straight line, which by the way is the most energy efficient. You don't need, but I foresee that if you need to navigate within the city, there is much more risks. That the drone crashes against the building, that it falls, it hits someone. So I think most of the studies and in the 3GPP assumptions is that the drone is always above the buildings, above the 22.5 meters.
Yeah, but you will only need to be higher than the highest buildings because you have very good line of sight.
Everything is possible. I don't know the answer, to be honest. It's the regulator, the one that will decide all of this. If I could be the regulator, I see that flying higher with clear sky should be easier than trying to navigate with some buildings. For example, I don't see helicopters flying within buildings. It's big. So, but again, I don't know. But this is the right thinking. The right thinking of people working in the willing to make money out of this is to think ahead. What if this happened? Make the analysis and then put the machinery of the company to work in that favor. So it's good to have these type of questions. But I don't know the answer.
In the project, there will be probably some testing in these highways, even would start in the campus.
Yeah, so we
plan to have a highway.
So we were talking with one of the professors here in the aeronautics department, and that he is involved in all this planning of highways in the future. That there will be a highway going from Lydia, I don't know where. And Narcis also proposed that we could do some of the studies in campus So emulate that we have, because Israel has permission or can easily get permission to fly the UAV, emulate that there is a highway, A2P within the campus, and using multiple base stations, for example, yours, we could understand handover problems, etc., etc. I don't think no one in the world is doing this type of things.
So I was telling this because there is a maximum and a minimum flying.
The flying is 160 here in Spain. 160, 200 meters around is the maximum that you can fly. And you cannot fly 5 kilometers within an airport. But here at the university, there is a permission because this and that. The people that has it.
It's not far enough.
For curiosity, the results you show on the presentation comes from simulation or real life?
This is a good question. So at that time, we have a team in Dublin. That was my team. And our expertise was mostly on simulation because we were working on a standardization. So we were thinking about new features that cannot be measured. So, but we had another team in Denmark where the expertise was to try out things in, like simple things in reality. So from there, what they did is to mount an iPhone and also a small cell into a drone. And then they used to fly the drone at different speeds, different heights over a lake. And then using those measurements, for example, we built propagation models. We built some knowledge of the distributions of the RSRPs, some very limited knowledge about the throughput. But the problem of those experiments is that how you're going to behave in a wide area network where there is many cells, you just don't know because you have just done an experiment and a very confined situations. So here it would be nice to do it in the university campus. More embed that those studies in Denmark were out of the city. Here, for example, it could be within the city of Valencia. It's a different. You will see more neighbors. So the answer is there was a hybrid, but most of this is simulation. Yes.
And in the new research that you want to perform, there is a model for the interference between the outer network, the middle, and or you are going to also to propose one, or how are the interferences there?
I'm not a channel modeling guy, although I've done some work on that. So the models has already been specified for this by the 3GPP. So there is a statistical channel model, a statistical 3D channel model. It is the 38901. And the plan is to perform all the studies using that model. Now, if there is expertise, so
because the fan comes when the interference come, because
if we know
the challenge is totally.
If we model the channel, so if I have a simulator that can simulate the network, the interference comes because another cell is using those resource blocks and it's interfering me. So I can simulate that interference. Now the true question is whether the channel model is right or not. For example, here was very in this analysis that Giovanni did, it was very interesting to see. Again, we know that, but this is not usually accounted in the 3GPP, it's the ground reflection. So the UAV was seeing the ground reflection. So again, measurements are important because you go to reality, you take measurements and you say, oh, they don't fit what I'm simulating. What is going on? And then you make the thinking, oh yeah, I studied in the UPV when I was the ground reflection might be something. And then you incorporate it and you see if. So yeah, you need to understand the channel, but because I don't have the capabilities and it's not my passion, let's say, I'm planning to reuse the 3GPP one. You guys have the ray tracer. We have means to perform studies on that. So I'm for it.
And another question: as you come from the industry, how extended is the deployment of the massive MIMO? There is a really commercial deployment of massive MIMO.
Yes.
Yeah. Here in Spain, or Okay.
all the operations they used. I mean, massive, it depends what you mean. It's not that massive, but it's quite massive.
Define massive.
Well, I can tell you, Huawei products, we had 196 antenna elements and 68 transceivers. 64, sorry.
And it's in several towers at the
Everywhere. Whenever we-
Phonica Vodafone.
Yes, that is
Okay.
deployed.
Up here, maybe.
Yeah, probably.
Okay.
It's easy to reckon if you see the antennas, it's like a small panel.
Not so much.
Not so much here.
I mean, yeah, what we will have, not so.
I don't think we have so many. I don't know.
In France,
I don't know.
in Paris, big time, and in China, everywhere.
Yeah, in Korea first, probably.
For me, I was with Huawei, and all the work that we did is to optimize networks in China. And 5G new radio, massive MIMO, 100 megahertz bandwidth, and 64. It was the start product.
Okay.
Yeah, otherwise you don't roll out. I mean,
What kind of simulator are you using for these studies? I mean, it seems to me that this is a system-level simulator.
yes.
But is a proprietary solution?
Yes. This was the simulator we had not yet.
Okay.
Wherever I've been, I would say if I have any expertise in simulation, wherever I've been, we have always had to create new simulators, build new simulators, customize it for the studies that we need. So there is not, I arrived to this company, they have this magic simulator that I put and I simulate. Because it's new technology, you need to always, so developing simulation tools. And now what I'm doing is developing a new simulator for me to perform the study. Otherwise, I don't have a tool. But I will make it publicly available to everyone. I'll be the first in the world. It's the ambition. The channel modeling is super important.
Muy bien. Muchas gracias otra vez.